I think everyone is filed in. Good afternoon. I'm Michael Cornwell with Microsoft Azure. I'm excited to talk to you today about software-defined flash futures and the things that we are doing around open compute, standardization, and maybe a little more detail about what was launched today in the keynote. So as part of OCP, Microsoft is a significant contributor. But the things that we don't usually talk about is the size of our fleet of SSDs, the number of systems, where they are, all of the things that are the nitty-gritty details that I think a lot of you want to hear from us. And we don't even tell a lot of people under NDA about our systems. But what we see is that computing has changed. And there's been, every decade has had a different change in computing, from the mainframe to where we are today with what we call ubiquity computing. And in every one of those cycles, there's a moment in time where the CPU can no longer keep up with the workload, and they go to some sort of I/O offload technology. So a great example, if you look at mainframes, they had this thing called IOP, which was an I/O processor. You look in the 90s or the early 2000s, tow cards, because Intel had to switch from a single core to multi-core. And we're running into the fact that Moore's law is giving up on us or slowing down. And whenever that happens, that's when you see breakthroughs in how people use I/O and how they focus on the efficiency of the processors more, and they focus on I/O being more, I guess, intelligent is the way to look at that. And so that's where we see that this ubiquity era is going to have the same features. And how you end up using storage will be really tied to how the application is developed, whether it's an IoT sensor, whether it's machine learning, or whether it's just your classical database. It all is done in a way that adds intelligence and adds scale. So last year, we announced Project Denali. And the hope of Project Denali, or the aspiration we had back then, is that we could convince the industry that we could break free of the monolithic storage device. For 50 years, we've had the same sort of interfaces to disk drives, whether it was blockhead sector or whether it was LBA. But there was this abstraction layer that made it impossible for us to know what's going on with our storage devices. So today, the millions of SSDs that we might have in our fleet, hypothetically, oh, we lost some video on that screen. There we go. And the hard disk drives all still have that same interface. And so what we wanted to do was to create a disaggregation, to allow a flexibility to deliver something different based off of the needs of our data centers. And that's where we saw the benefits of what Denali delivered. That traditional block interface disappearing and not having to guess what's happening with inside the storage or where we're writing our data, but actually know. Other people have tried this before. So open channel SSDs and this open channel interface where you remove all of the intelligence became very hard because you had to manage all aspects of the media, and more particularly bad blocks. So managing bad blocks can be a very hard, cumbersome project for a SSD firmware. And so that's where we see that being able to break those things up to have the FTL independent of that became very powerful. Being able to control the garbage collection. This is our biggest problem of quality with SSDs for the last decade, is that once the SSD is dirty, it has to go clean itself. And when it goes and cleans itself, it degrades performance. And no matter how many different ways people have talked about how they can make that not happen, all SSDs have that problem. And it's a big problem if you can't tell when it's doing it. And then the final one is really around cost. And what SSDs cost is really being driven at high capacity by DRAM more than flash. So if you look at most SSDs have this rule, this golden rule of 1 gigabyte per terabyte of flash. So if you were to say, I'm going to build a 32 terabyte SSD, you have to put 32 gigabytes of DRAM on it. At, say, $10 a gigabyte, it becomes a significant cost. And so having a more efficient and effective way of managing that is a real benefit, and that's where we see a lot of COGS savings. And then finally, being able to have this thing configurable. So if we're running a database workload, have a configured FTL for SSD specifically for database, or have it for virtualization, or for AI, or for any of our other services, and have the ability to change that in order to match the durability and the performance without having to have multiple different types of SSDs in our systems. And this is also a bit of a refresher, which is how we saw the architecture, is moving from a monolithic architecture to having something that is software defined. And what we're seeing in the cloud space is that there is a lot of focus on the software defined model of Denali for a lot of traditional applications like databases or SQL or applications that already are managing metadata. They don't mind managing a little more metadata. But what we're seeing in applications like virtualization is those applications don't want to use host I/O or host compute to do the processing of data. And that's where this idea of an aggregator solution or an SOC solution, something that is able to aggregate it, becomes a very powerful model in how Denali gets used. And so breaking those two models is we have to look at how do we support both of those. And how can you build an ecosystem around that? And that's why we're presenting here to you today is we see that there are a number of you and a number of partners out there who are building ecosystems around this. There's some great startups building SOCs, and there's some great startups building software to manage these types of devices. So here is our report card. Denali is one of the fastest specifications that's been done. To do a specification from start to finish within a year, if you go look at Ethernet and how long it takes them to get things out, or Wi-Fi, or some of these other standards, we were able to move very fast and very quickly to publish the spec that we published today. And that specification is on GitHub. It's available today. And it is a good configurable platform for a number of type of applications, from enterprise storage arrays that want to manage their own metadata, to databases, to even IoT devices. A lot of mobile devices are now very interested in this type of architecture because of what it can do to save DRAM and save costs within those systems. So this is what we ended up building. This is our Denali Prototype SSD. Microsoft partnered with Phoenix Labs, Lite-On, and Toshiba to build what we saw as the first building block to understand how to deploy and use this technology. So a bit of the speeds and feeds of this. This is actually 2 SSDs in one. So there is one SSD that's 8 terabytes on one side. You flip it over on the other side, and there's an 8 terabyte SSD. We did that for performance because the EDSFF 1U long form factor has the ability to have 2 SSDs independently talk across the interface. So this allows us to package and have a very lightweight, cost-effective solution that is incredibly performant. And we're able to do the configuration of what we need to do from a DRAM cost standpoint, depending on the application, and also from a performance standpoint. So I'm big about handing these things around and doing a little show and tell. Please make sure that this doesn't end up in somebody's bag as it gets passed around, or I might get in a little trouble. And this is a building block that we designed because we have an ecosystem already around EDSFF 1U long. So if you recall or were here at OCP last year, we talked about our FX16 platform, which was the first platform to use this new form factor as a building block within the OCP ecosystem. So you're able to remove a standard NVMe 1U long SSD and put this in. And then what we were also able to do is we've designed it so we can reconfigure the SSD from normal NVMe mode to Denali mode so that we don't have to worry about having to go and replace it. So as we want to go and reprovision it one way versus the other, it's actually very simple for us to do that through how we do firmware updates and those types of things. So with this disaggregated model, and this is the way that we are looking at how to do this disaggregated model, which is the FX16, and then this idea of a virtualization controller. Some people in the startup community is a buzz right now of this new word that they all think they invented called data processing units, or DPUs, where DPUs have been around in mainframes for a very long time, but they've reemerged in the new generation. And it's basically, the way I think of it, is what a RAID controller was in the 90s is what a DPU is today, which is how do you do intelligent aggregation and application processing on something external to the storage, but also external to the host. So in that virtualized controller, you can virtualize NVMe devices. You can basically have RAID. You can do all sorts of things at a level that is not looking at it as a bunch of SSDs, but looking at it as the individual flash die. And that's critical to how you want to go and do data layout, data protection, performance of devices. And the board that's actually above the virtualized controller, that's actually a board that our MSR research team is using to optimize applications on these types of devices. So it's effectively a PCIe to PCIe controller that they are embedding applications, and I don't want to steal their thunder or say any proprietary information, but that's how we're looking at how to optimize these devices, is that you can put the awareness into the FTL that's actually running the system. So in the case of search, you can actually embed the search characteristics or attributes into the FTL. If it's key value store or blob, those types of things, you can actually just embed it physically into how you connect and read and write from the device. The key thing here as well is that NVMe is the interface to these devices. And I caused a little bit of controversy at another conference with this slide, which is that NVMe is not a storage protocol. NVMe is a transport. And how you should think of it is exactly like you think of TCP/IP. Everyone hates TCP/IP because it's very slow, but it's the way that we do interconnect of applications that ride above the networking protocol. The same thing is true of NVMe. And so what we're seeing now is that there's an emergence of applications that are driving things on that transport layer. And those applications are what we call computational storage devices, or computational SSDs, so that you're able to use that transport layer in order to send commands to those devices and do things with them. And the whole idea here is as these devices get larger and larger, it's harder and harder to get data out of them. So you want to be able to, the gravity of that data in the environment is what you really want to focus on. So for example, if I had images that I wanted to search, I would load through the NVMe interface some sort of pattern matching awareness to that SSD. And then the SSD, instead of giving me data out through the LBA interface, would just go and search and look for the picture, or go look for a piece of metadata in a blob store. And so this area of this emerging technology is the most exciting for us. And there's a number of the computational or offload-based storage device companies here today at OCP. I think there's a number of them on the floor. But this new era of these devices that are aware is really exciting. But it also comes with some challenges. So if your storage device isn't just reading and writing blocks, but it's actually reading your data, you have a security problem, which is that that device all of a sudden has the ability to go read bank records and databases rather than just read and write the I/O back to the secure database. And that area is our biggest challenge in looking at these devices. Because if you have to go and we encrypt something down to a storage device, in order to decrypt it to use this type of computational technology, you have to pass down the key. And then you have to have key management. And then you have all the pieces and intricacies of how to remove the key once you've actually found the result and then handed it back to the host. And in a lot of cases, you would actually have to encrypt the response to go back to the host because you're over some sort of public cloud or some public network. So there's a lot of areas where this area of these new classes of storage devices, which we're very focused on when we look at Denali and how Denali gets implemented, but it is something that still has to get sorted out. So there's some great working groups that are already doing this in SNIA, and we are very supportive of what they're doing in driving the awareness of this and the standardization of this, again, on top of NVMe. The final is, where do we go from here? So as we look at what we are doing with this aggregated solution, it became very clear to us that we have a great platform in this EDSFF form factor to be able to shrink all this into a single thing. So instead of having an external SOC accelerator, well, we can just put it on the board. Instead of using form factor SSDs, well, laptops and cell phones use these great SSDs that are a single package BGA with a controller in it. They're cheap, they're power efficient, and they allow you to do the autonomous things that we want to do. So when we look at where we would want to go with Denali, one of the places that we're looking is to go look at UFS and build along the handset commodity trail, because those devices are very cost effective for a reason. And they don't have all the intelligence that a traditional SSD has, because in a cell phone, they're managing them themselves. And so this is the type of prototypes that we're looking at generating next. And then for the vendors out there that are working on these DPUs are a great, make sure you package your DPUs in a form factor or a package that could fit on an EDSF ruler. Because if you look at where other people are using this technology, that is a very powerful and effective way to prototype a lot of the new DPU type applications without having to worry about having many different types of storage. You can basically build it all into a single package and make it plug and play with an existing SSD today, with having a lot of vendor unique capabilities that let you drive into new environments and new types of application acceleration. So I deliberately left my presentation a little short because there's been a ton of questions about Denali today in our booth, and I just wanted to use this forum to maybe have 5 or 10 minutes of questions of what people wanted to ask us about what's happening with the spec and where the specification is going. All right, so I think we have the microphones, might be the easiest way. In back, yep. Mr. Coughlin.
Indeed. So I had an interesting question. So I kind of thought the computational storage and the Denali approach were kind of different sides, you know, but you seem to be saying that you actually can bring together the computational storage with actually taking processing off of the SSD. Is that correct, or tell me about what you're getting at there?
Yes, and I think that's where we are looking at this ability to do disaggregation. Is one of the biggest blocks that you have in an SSD controller is the ECC. And you want multiple of those blocks in order to have parallelization of performance. And so that's where we see it as more of a 2-chip solution than a 1-chip solution, which is a lot of computational SSD providers are looking at a 1-chip solution where they have everything you need with a standard SSD, and then they go add a couple of extra ARM processors in there.
So it really is kind of just a part of a gross disaggregation of where the computation is going on and bringing some of it close to the storage. Is that?
And that's correct. And the nice thing about it is that there's no right or wrong architecture, because the interface is the same interface. Yes? So that's where Cerberus is our OCP, or the part of the broader OCP community on focusing on root of trust of the firmware. But what we see is a big gap in current looking at computational SSD is there's no common way to do key exchange. And that's going to be really important for being able to have encrypted workloads. In scientific environments or image search, it's not as important. If you're searching, again, financial data and personal data, you'll want to have a way to do that. And right now, computational SSDs, in my mind, I haven't seen a great standard. Stephen?
Working on it.
He's working on it. So Stephen's working on it over here.
Yeah, I was just going to ask, can you explain this picture a little bit more?
Yeah, so picture is effectively that shrunk. So there's a host, there's a virtualized controller with media SSDs with DRAM that is all pushed onto a single PCB. And so all of the UFS SSDs would connect into the Denali SOC, and then the DRAM is used by the Denali SOC. And then the interface going out is the standard NVMe EDSFF EDSSF E1 long interface that, again, looks like a standard NVMe device, but then has vendor unique capability. Yes? You could do it. We see this as having a two-chip or a multi-chip solution, where in the Denali model, we're disaggregating the media characteristics or the ECC and the media management independent of the application. And so that's why this model for us is the two-chip model of having a media SSD and then a Denali SOC enables us to have, again, it's like you said, it's the same functional interface, but it gives us a lot more flexibility with the benefits of Denali.
Hey, so Kusakra, during his presentation, mentioned something about Denali and zones, zone namespaces. What is the relationship between that?
So there's a number of efforts on using Denali type characteristics of multiple different interfaces. And so zones is one, the SMR is the other from the T13 and T10 for disk drives. And Lee Pruitt is giving a talk actually tomorrow on our strategy on how we see all of these ecosystems aligned together. So I think there's a case where that zoned interface would be the interface out to the host, where we would still have Denali media SSDs internally. Yes?
You mentioned a ratio of 1 terabyte to 1 gigabyte to the host, and what is that? How does it change with Denali? Because it's now on the SoC itself, it's on the chip itself, and it's closer. What does the host need now?
Well, the reason that FTL 1 megabyte to 1 or 1 gigabyte to 1 terabyte is there is because it has to present logical block addresses, and because you're presenting logical block addresses, you actually have to have a physical space where you can map 4K sectors into that FTL. Part of what this type of technology allows you to do is that you can actually free yourself from talking to LBAs and have very precise static mapping of the geometry of the flash. So that's where the DRAM reduction comes from. Stephen.
Michael, thanks, great talk. You mentioned encryption as one of the challenges when computation is really close to the data, because we typically manage that on the host. But also sometimes we put data distributed across multiple devices in the same server, so RAID striping or some other kind of data spread. Does Denali take that into consideration if the compute is on one of these drives but the data is distributed across several, how we kind of aggregate back to get the data we need to work on?
That is really, we see as a higher level function. So how data is placed into a SSD or a Denali SSD is really left up to the application. And the application should be aware of how data is spread either in or out of a given domain of SSDs. All right, last one. Yep, last one.
Yeah, one question about compression. So do you have a few more words about it? Where does it happen and how does it interact with the rest of the system, the host versus the SSD?
So where we see things like Zipline, and Zipline is a powerful technology for SSDs, and part of the open source as part of OCP was so that people could embed that technology into SSDs. So we see it could be at the SSD level, it could be at an aggregator level. Likely we would not put it into the UFS or the media SSD, but you would want that intelligence to be able to live in the higher levels of the stack, because once you encrypt and then compress data, you typically would want something to store that very effectively.
Thank you.
Well, that's the last question. So thank you very much for your time this afternoon.